Okay, what I just mentioned was we're doing model building. Everybody got 10 points yesterday, but if you're not here for model building, you're required to do the model building. So when you get back, you'll have to do that. If you want to be creative, you want to go get some gumdrops or some colored candy, and you want to build along with me and send me a video of you building the models, I'll give you your 10 points. So if you want to do that, you can do that. All right, here we go. All right, so we're gonna, I'm gonna flip this paper back over a little bit. And excuse me. So we talked twice about why are there so many? Why are there so many carbon compounds? So if I were to ask you that, let's say I had a quiz or something like that, could you come up with at least 3 good reasons why there's so many carbon compounds? So, well, all right, what do you think, Carson?
They only have 4 valence electrons.
Only? Or that's a lot, actually.
Well, it still leaves room for them to get more or less.
Right. So a lot of things, and when you have more than 4 valence electrons, you tend not to share at all. You tend to just lose them. You lose 1 or lose 2 or lose 3. I'm sorry, gain 1, 2, or 3. But carbon's right in that middle section where he can gain or lose. But if he wants to gain, he can actually form bonds of 4 different atoms. And that's a small thing, but what else? What else can carbon do?
It's not very reactive.
Is that why there's so many compounds in? I wouldn't put that down. If they said, why are there so many carbon compounds? You say, because it's not reactive. Well, why are there so many compounds in? Yes?
It can bond with itself in single bonds, double bonds, or
That's right. What else?
It can have the same amount of hydrogen and carbon, but it can rearrange into different compounds.
What are those called?
Isomers.
Isomers. And it's not just carbon and hydrogen. You can put a chlorine in there and have an isomer of that too. So isomers are really, really big as to why there's so many. You get that? We also, there's one more thing. They can build long chains, right? And what kind of chains? What do they call them?
carbon backbones.
What?
Carbon backbones, is that you're talking about?
Well, straight is one. They can build straight chains, or what else? Branching chains. And what else can they make? We're going to make some of those today. Ring structures. We're going to make some of those today, okay? All right. So when we go down here, I want to mention another thing is when you see this is the molecular formula. Is that correct? We did a lot of that yesterday. Molecular formula, that's just a CHON, whatever, Cl. And then you have a structural formula, which is almost like you drawing it out on paper, isn't it? It tells you how to build it together. And that's kind of what you're doing with the model building. And then you have the graphic formula. You want to get, every time you build a model in here, say, do I know how to do the molecular formula? Do I know how to do the graphic formula? And just kind of start left to right, like CH3O, CH3. This one, CH3, CH2, CH2, Cl. Everybody got that? Now, when you come down here, you're going to figure this out. A lot of you already figured it out, but in the middle, you have CH2s most of the time, right? But what if you did this? What is the graphic formula here? CH3, CH, CH3. What's that? See, you normally wouldn't find a CH3 in the middle unless it's a branch. See that? You can't have a CH3 in the middle unless it's a branch by itself. So CH3, CH, CH3, CH3. So whenever you see CH3 2 times in a row, it's got to be a branch. All right, see okay now? Now, the next thing I'm going to show you, and I did this the other day, is we have this model. What kind of a model is that? That's what you're building. What are they called? What is it? Well, that's the shape of that one, but what do you call any of these? What I use, this is the ball and stick model, okay? Now, some books will use diagrams that are ball and stick because they want you to see all the atoms and they want you to see all the bonds. But then you'll get many of your college textbooks, especially like in biology class, they'll do things like that, or they'll do things like that. And they think you have to know enough to know, well, how many bonds does oxygen want to form anyway? 2. So there's 2 single bonds there. I don't need to show you those sticks, do I? Because you're supposed to know there's 2 single bonds there. What about this? What about CH4? How many single bonds? Any double bonds? No, it's all single bonds, right? So then they use this because a space filling model is a little bit more realistic as far as what the molecule looks like. So I'll be somebody with I never got to build models. I didn't know exactly, when I saw those in the book, that was like over 40 years ago, I saw them in the book, and I didn't know what some of those things were. So, okay. Are you ready? All right, let's turn over now. We started a series, and we found out that a hydrocarbon only contains hydrogen and carbon. That's pretty good, right? Pretty easy. You probably remember from another chapter that hydrocarbons, because there's kind of equal sharing between the carbons and hydrogens, all of them are non-polar, so they wouldn't mix with water. Another thing they have in common is that they're all flammable, so you can pretty much burn every hydrocarbon you can make. Okay. Now, what's interesting is what happens as you make a longer and longer hydrocarbon chain. And the memory trick here, if it's a saturated hydrocarbon, it's all single bonds. Everybody got that? So if it's saturated and it's only a hydrocarbon, we call it an alkane. Now, all the alkanes end in ane. That's easy. And you just have to memorize the prefix, and mother eats peanut butter, whoever eats peanut butter, mom, Michael, whoever. If you remember the first four, your geometry will probably kick in here. Pentane, pentagon, right? That's 5. Hex 6, hept is 7, oct is 8. Everybody got that? So I think you'll probably get those. Yes.
Can you spring water, please?
What happened? Oh, I apologize for that. Sorry. Thanks for doing that. Thanks for telling me that. All right. Now, we saw a pattern yesterday, didn't we? What was the pattern for the alkane series? And I even asked you a question. Let's try it real quickly. What about alkane with 50 carbons? What would be the molecular formula? C50, how much? 102. And so it's CnH2n plus 2. Now, I know some of you have been in school for a long time. You said, oh, I better memorize 2n plus 2. You can memorize it, or you can think about the models you're building. When you made pentane, didn't you have every carbon had 2 hydrogens on it? Except the ones on the end? 1 extra one here, and 1 extra one here? That's that plus 2, isn't it? That's where they get the 2n plus 2. It makes sense to be 2n plus 2. It's not you have to memorize it. Okay, so are you okay? Now, another thing, now this goes way, way, way back into physics, where the kinetic energy of a particle is 1/2 mass times the velocity squared. Now, what you know is that at room temperature, everything has about the same kind of kinetic energy. So what happens if you have something that has a greater and greater mass? So if this is held constant, and you have, if your mass goes up and up and up and up, what happens to the speed of the particle? It goes down with the square, doesn't it? So these big guys, if you could see them, they're bouncing around not as fast as the little guys, right? But even this big guy here, even butane, as big as he is, he's still fast enough to not become a liquid. You get that? So what's the first alkane that is big enough, is slow enough, that it's actually is a liquid, and that is pentane. Now what will happen is, you've seen butane lighters, and it looks like they're liquid, but they're under pressure. So under normal pressure, they're supposed to be a gas. And if you hold it open and don't spark the spark, psst, it is a gas, isn't it? It's just under pressure is what makes it look like liquid. Some of you have gas grills at home, barbecue grills. Do you have those? Have you ever been the person to go get another tank? Did you ever move the tank around? He said, did you feel the liquid in there? Well, I thought butane was a gas. It is. When you open up the gas and don't spark it, isn't it gas? Then what's that liquid in there? When you move that big tank, why does it slosh around?
Pressurized.
It's pressurized. Okay, and when you later in the year, when God willing, when we do a chromatography project, I will give you different kinds of solvents. And water's a solvent, but also they're organic solvents, and this is one that I would use called hexane. It's in a bottle, it's a liquid. So I can actually show you hexane, it really is a liquid. Yes?
Do they use propane in propane tanks instead
Yeah.
of the instead of the ones that are naturally liquids because they can fit more?
Right, if I wanted to transport a lot of propane across the country or across the state, they have refrigerated and pressurized tanks. They're pressurized and refrigerated so they can even squeeze even more. Yes, they would be very dangerous if somebody were to blow them up, yes. But they actually be able to transport huge amounts of gas in those tankers if they're refrigerated and pressurized. That's a great question. Okay, ready? Are you ready to build some more? Yes.
How often is hexane and like the other hydrocarbons that are liquids? How often are they used as solvents?
Okay, in the world you live in, you're going to be mainly in the water world.
Right.
We don't like putting our hands in gasoline, or we don't like that kind of stuff. And but if you become an organic chemist, or you work in an industry that has to do with plastics or rubber, or you'll find they have huge tanks of these different solvents. One of them might be hexane. That's a pretty common one. When I went to college, we had to clean, we took organic chemistry, a lot of the stuff wouldn't clean very well with water. So we used the organic chemistry water that was called acetone. You'll find out what acetone is later, but it's an organic solvent that they used to always put it in fingernail polish remover. I'm not sure if they took it out or not, but anyway, it used to be in fingernail polish remover, and it was really good at dissolving organic things like that. Okay, yes, one more question, then you move on. Let's build some models.
Does the flammability of them change?
Well, I would say, like, that's a good question. I don't know. I don't have a chart with me. They're all flammable. When you say, does the flammability change? Well, they're all flammable. But I think what you mean maybe is how much heat is produced per, something like that. I'd have to look that up. I'd have to look up, like, how much heat is produced if you combust 1 mole of that, 1 mole of that, 1 mole. That'd be the molar heat of combustion. I bet that's the name of it. You want to look it up? Molar heat of combustion, organic. Let's say organic. Okay. All right, let's go on. So we built methane. Is that correct? Okay. How about methane? If we want to go into the next of the hydrocarbons, it's not the alkanes, but the alkenes, and we're going to keep it to 1 double bond. Okay. So I hereby declare that for right now, all the alkenes have only 1 double bond. So let's make methane. How soon we forget. Okay, well, you can't make methane because you have to have a double bond. You only have 1 carbon, so there's nobody to double bond with, right? So what's the simplest alkene that we can make? Ethene. Let's make ethene. Everybody make ethene. That's it. And now you know what the little sticks are for now, right? The little sticks are flexible. That's it. That's 2. You're almost there. If you beat this other table, I'll know it wasn't Caroline yesterday. I'll know it was Caroline's fault yesterday. Okay, now how are you going to put a double bond on that? That's it. You got to use the skinny guys and put another skinny one. Get another skinny one. Get another skinny one. That's it. Is that a skinny? Yeah. There we go. Hey, you can't have any open holes. There's no open holes here. All right, what do you think? Ethene. Yes, no? Okay, now, let's make, ready? Let's make propene. See if anybody's ahead of me. No, they're not ahead of me. All right. Let's make propene. Just 1 double bond. Oh, by the way, I'm sorry. Let's stop just for a minute. What was the molecular formula for ethene? C2, H what? 4? Okay, now let's make propene. Every time we build a model, say, what's the molecular formula? what is the graphic formula? What's the molecular, what's the graphic formula? Yep, that's it. Now, tell each other what the molecular is and what the graphic formula is, okay? And hey, you know what? We're looking for a pattern. We're looking for a pattern. All right, let me call on Jeb. Jeb, what is the molecular formula? Yep. Say it again. C3. H6. Okay, now, Caleb, what's the graphic formula for propene? What's the graphic formula?
C2, there's CH2, CH2.
Can you hold your model up so I can see it? All right, what is it now? Just look at the model. What is it? CH3, CH3, CH, and then CH2? Okay. Now, can everybody stop for a second? Now, we're going to build one more. We're going to build one more. Oh, wait, that's not right. Can you build an isomer of this propene? Now, you can't lose any atoms. It has to have the same molecular equation. Formula, I'm sorry. It has to have the same molecular formula. Is there an isomer? Is there an isomer of propene?
Or you can't like make another double bond.
No. Well, you have to have only one double bond. Well, I didn't say that. You just can't lose any atoms. You have to have the same molecular formula. What do you think? All right, big X. You were right yesterday with a big X. Today you're not. What do you think? Can you make an isomer of this? Okay. All right. Can I have one of yours throw it to me?
Yeah.
Good. I get you. All right. Now, little trick question. Trick question. Ready? Let me show you what happens here. Oh, wait a minute. No, wait a minute. I made a mistake. Wait.
It'd still be the same.
Well, if you make another double bond, you're going to be getting.
No, I'm not gonna do that. C3H6. Oh, wait a minute. What happened here? Let me think about this.
Either way, don't lose because you can see like.
Let me think about that.
Yeah, it doesn't matter. If implicitly, you can't because of this. There has to be a double bond already in it because there's not enough hydrogen to fill the cell.
Wait, no, that's not a double bond.
Guys. I see one atom with two things to do.
It's not a double bond.
Where's the double bond?
All right, I'm impressed. I had a little trouble. Wait, here it goes.
Wait, where's the double bond?
I didn't say that. I said, can you make an isomer? What is what's the only requirement? What's the only requirement? What's the only requirement for an isomer?
So you said with the double
Same molecular formula. There it is. I'm impressed. So, what I want to show you is that what was the pattern for an alkene? What's the pattern? What if I said you had an alkene that had 10 carbons? How many hydrogens would be in an alkene with 10 carbons? What's the pattern? What is it? Everybody got that?
Yeah, but you.
So what happens is, and this is what I want you to learn, okay? You paid a price. If I were to make propane, and I turned propane into propene, I would pay a price for that double bond, wouldn't it? What price do you pay from going from propane to propene? If you go from propane to propene, what price do you pay? Yes, you're really picking up on this. There's a price to pay. When you put a double bond there, you lose 2 hydrogens. So if this was CN, H2N plus 2, this is CN, H what? 2N without the plus 2. When you put a double bond in there, you pay a price. Now, we're going to make some ring structures today, and I just want to whet your appetite for that a little bit. What price do you pay when you make a ring structure? You lose 2 hydrogens. So anytime I see a double bond, I know you could make another isomer by getting rid of the double bond and making a ring structure. So we'll talk about that a little bit later. Here you go. All right. Now, let's make, oh, by the way, wait, let's start here. Can you make an isomer of this that's not a ring structure? No, because the double bond here is the same as what? As the double bond over there, isn't it? See that? So in this case, there are only 2 isomers of that. This one and the ring structure. Everybody got it? All right, let's go on. All right, let's make ethine. Let's go to the alkynes. All right, let's make ethine, and, well, you're ahead of me. Very good, very good. And don't take that apart. Hang on to it for a minute. Yes, yes. Make ethine. Get your fingers out of the way. There you go. I can see it now. Ethine. Ethine. That's it. That's it. 2 more tables. 2 more tables.
The other one was the I made up. I don't know.
You got it? Yes, that's it. That kind of looks, doesn't it remind you like a spaceship?
Yeah.
Hey, you know what? I'm a little bit surprised. Hey, can I have it? I'm a little bit surprised. Usually, long before now, someone's made a little dog or nobody's making any. Okay. I'm all right with that. You can have some fun, but usually by now, somebody's made a little dog or an elephant or something like that. But that's all right. So, all right. I haven't seen your ethine. You got ethine yet? You're getting there? Okay, you're going to have to use 2 more skinny guys. All right, everybody stop. Now, I could make propine, and we could go in and make butane, but my question is, what is the pattern for the alkynes? What is the pattern? And I know you can look down here, but when you're building models, you know that the ethines were CnH2n. And then you put another bond on there. What's the price you're going to pay for that? 2 more hydrogens. So what is the general pattern? Cn, H what? 2n minus 2. I'm looking at your faces, so I can't tell if that made sense to you. All right. Okay. Now here's something that I don't like about organic. I thought they did a great job when they started naming them. They kind of made a very logical thing. Unfortunately, just like inorganic chemistry, like for example, what do we call H2O? We should call it dihydrogen monoxide, and we don't. And what about NH3? We call it ammonia. It should be nitrogen trihydride. And there are lots of things that have, they shouldn't have said hydroxide in the IDE. There are some mistakes they can't fix. In the world of biology, there's little insects. I was in the attic last weekend and I saw a couple silverfish. They aren't fish. Okay, there are a lot of bad names. Starfish are not fish, and seahorses are not horses. They're fish. And so we have a lot of bad naming in the past that it doesn't go away. Isn't that right? Okay, now, look right here. All right, everybody stop. This right here is a very, very important chemical in the world you live in. So what's going to happen is, even though you would call it ethene, if you look at any book more than 30 years ago, and even some modern books, another name for that is ethylene. Now, what's going to happen is, the reason I need you to know that ethene is the same as ethylene is later we're going to put a whole bunch of ethenes together. We're going to make polyethylene. And polyethylene is one of the most famous plastics in your world. Okay? And so you have to know that ethene and ethylene is the same name. Now here's one I really don't like. Here's one I really don't like, and it's just one of those things I have to learn about. Ethyne is a great name. If you say ethyne, you're okay. But I don't know if you'll ever see anybody in the real world out there calling it that, because when they learned the name, it was called acetylene. And the old way of saying that you contain two carbons is aceto. Now, the new naming is eth. You see that? So there are some leftovers. Now, have you ever heard of acetylene torches? Acetylene torches, that's what they're burning. And that'd get hot. But if you want to get them hotter, here's what you're going to hear on TV sometimes. If you want to go right through thick steel, they're going to bring in a tank of pure oxygen and put it up with the acetylene. They're going to have called an oxyacetylene torch. An oxyacetylene torch is where you have pure oxygen being poured in here, and it burns at such a high temperature, it can melt right through steel, thick steel. So acetylene torches have been used for a lot of time. Oxyacetylene for some major cutting through steel, things like that.
Wouldn't it match pretty close to plasma levels at that point?
I could see that. I'd have to look up the temperature. It's way up there. It's way up there. What is acetylene in air temperature versus acetylene in pure oxygen? I don't know that. Again, you can look if you want to look some of those up. You have great questions. All right, are you ready? Now I'm gonna come back to polymers later. So I think we're ready to build some more models. Let's go over here. All right, really, I'd like you to make methane. Let's make methane again. Ready, make methane. All right, there you go. Make methane. That's it. Okay. Now, I really, I feel very strongly that you know how to make methane now, right? Does everybody have methane? All right. Now, why am I going all the way back to methane? Because I want to show you another realm of organic chemistry, not just hydrocarbons. Matter of fact, some books would call these substituted hydrocarbons, or they might call them, functional groups. So what we're going to do is we're going to take something called methane, and we're going to change something. So is everybody ready? Everybody have methane? Now, nobody's ever made inchworm so far. That's the first one I've ever seen. Okay. Or a footworm. Here's a footworm. Okay, here we go. Ready? In the world of organic chemistry, if you have a hydroxyl group. Now, if you've been doing your reading, if you've been reading in your packet, you know that a carbon attached to an O, attached to an H, this right here is called a hydroxyl group. I'm sorry. Did I say hydroxyl? Hydroxyl group. Now, what I'd like you to do is to take one of your hydrogens off of your methane and replace it and make it a hydroxyl group here. So make it like that, okay? All right. Everybody got that? That didn't take very long. That's good. That's fast. That's right. Yes. That's it. One more. Two more. Got it? Okay, now, everybody ready? Let me see. That's it. All right, now, what you've done is made the world's simplest alcohol. Now, what they did is they decided not to call this Bobby Sue. They said, what are we going to call it? It's not methane anymore. It's now an alcohol. Look at me. It's an alcohol. So we'll call methane turned into methanol. Okay, so you just made the alcohol called methanol. In parentheses, you'll see another name. What's another name for methanol? Methyl alcohol. Are you okay with that? That's not that big a stretch. Methanol, methyl alcohol. Now, this kind of alcohol, if you've been doing your reading, this is not what you want to put in your body. You can buy it at the hardware store. It's great at a solvent. It'll dissolve some oil-based paints. It'll, clean your brushes if you have oil-based paint. But you do not want to drink this. In your book, I think it said a tablespoon. Was a tablespoon enough to make you go blind, and a little bit more you die?
Like 15.
Of all the alcohols, and I'm surprised God let us drink any alcohols, but this alcohol is not the one that you want to drink. It would cause serious damage. And it's interesting that the simplest alcohol can cause huge damage, but the one right next to it, ethanol, is the what's found in all these drinks. All right.
How does it take apart oils and stuff? Like, aren't oils
Okay.
sometimes-
All right. Let me. I'll have to get back that. Can I?
Yeah, you're fine.
All right. So we know that a lot of organic things are not. Well, this one's actually a little bit polar because it's an alcohol. So methanol would mix with water. It would mix with water, but it also seems to be able to dissolve other organic things. That's a good question about what properties of methanol make it good at dissolving that. I'm not sure I know that. All right, what I'd like you to do now is make ethanol. Let's make ethanol. Make ethanol. And at this point, we're only going to have one of those OH groups on there. Only one. That's it. That's it. Make ethanol.
Isn't this just a carboxyl group?
We're going to make that later. This is hydroxyl.
Like, carboxyl COH?
Yes, COOH.
Oh, that's what it is.
Yes, ethanol. Yes, that's it. Got 2 more tables. Ethanol. That's it. That's it. That's it. That's it. One more. One more table. All right. Now, you got it yet? You got it, Gabby? Your fingers hurting? Ethanol, 2 carbons. Hey, whenever you're making these, everybody listen. Hey, I know. Whenever you're making these, honestly, if you do the carbon backbone first and then start attaching things to it, it makes a lot more sense. So I would have had, actually, if I would have had my methanol, I would have just taken that OH off and put another carbon on there, OH, and then filled it in there. Now, what's the other name for methanol? Ethanol. I'm sorry. What's another name for ethanol? Ethyl alcohol. Now, ethyl alcohol is the alcohol that's found in beer and wine and these hard drinks, the liquors. Okay, remember, got that? If you did some reading in your book, you know that some of the hard drinks have a rating. Maybe they just thought, hey, people get alcohol for this kind of stuff. They don't want to be scientific about it. But what they do in the store is if it says something like 80 proof alcohol, you cut that number in half, and that means that every bit of that is 40% alcohol. It's 60% water, but that's 40% alcohol. Let's give you an idea. Beer can be like 5 or 6%, and some wines might go up to maybe 13 or 14, but beer and wine are in another category completely than something that's like 40% alcohol or 50% alcohol. Okay, everybody stop for a minute. Everybody got that? So if you're doing your reading, you've already read the part with alcohol, you might have seen that thing about proof. What they did at one time is when people were making their own alcohol, and they still do, people, you know humans. If I made 3 gallons of alcohol and I sold them, I made a certain amount of money. I said, wait a minute, what if I dilute the alcohol and I can make 5 gallons of alcohol out of the same 3? And you still buy it. What happens if you still buy it? I just made more money for the same amount of alcohol. What if I dilute a little bit more? Well, then sometimes you have to wait until the customer starts saying, there was something wrong with that last batch you gave me. I don't know how much alcohol was in there. Prove it to me. And what they would do is take a little gunpowder and put that on there, and if it didn't light, that was proof. If it lit, it was proof that it had a certain amount of alcohol in it.
How do they test it today?
You what now?
How do they test the alcohol today?
All right, today it's all about density. They call it specific gravity in the industry. But you know what? Instead of taking some out and doing the mass and the volume, they have these neat little there are glass tubes that have there's one for milk, there's one for beer, and all you do is put it in there, and it'll go like this, and part of the stem will be sticking up. And if it's in between these two lines, it's about 10% alcohol. And they have another one. I had a parent, actually this building's named for that parent. I had a parent who was, and legally you can make your own alcohol, does everybody know? And they were going to test their alcohol. And so we happen to have an old one of those specific gravity things, and he had to buy his own because he wanted to be exactly a certain percent. And you just plug it, you just put it in there, and it floats, and the amount that sticks above, and you just read it like that, and it tells you exactly what percent alcohol it is. That's how they do it now. It's all about density. All right, now, does everybody still have their ethanol? Now, my question is, can you make an isomer of that? Is there an isomer of ethanol? I like the fact that some of you are turning it around, upside down. Okay, all right. Now, can you tell me what the molecular formula of that is?
This, C2.
Wait, see what now? Wait a minute. See what? H60, is that right? All right, so what do you think? So, hold it up in the air, okay? Can you hold it up in the air? So that has the same formula as ethanol, is that right? Okay, now we haven't learned what that is yet, and we will. But there is an isomer of it, but it's not an alcohol anymore, is it? Look at it. Is that an alcohol? Okay, now, you don't know what these are yet, but eventually you'll learn that when you have a carbon, oxygen, carbon, it's called an ether. And so what you did is, you did make an isomer, but it's not an alcohol anymore. And we'll find out later that's called dimethyl ether, and we'll do that later. Okay, now, let's make propanol. All right, go. Make propanol. You guys are fast. You are fast. Propanol. That's it. Okay, that's it. Very good. Propanol. Got 2 tables. 3 tables. Propanol. Now, while you're sitting there waiting for everybody to finish, here's what I want you to do. You and your partner, you say, what is the molecular formula? What is the graphic formula? What is the molecular formula? What is the graphic formula? There you go. Wait a minute. Oh, you made a different one. Ooh. All right, hang on to that. Hang on. You made one different than anybody else. How we doing? Yeah, how you doing on that? Okay. Now, wait a minute. You can't have any open holes. All right, question. Can you make an isomer of this that is still an alcohol? If you can, do it. If you can make another isomer of this and it's still an alcohol, then do it. Oh, you guys are really picking up things fast. That's one of them. Now, can you make an isomer? That's it. That's it. Wow, you guys are picking up on this very fast. Very fast. All right, 3 tables have gotten it. You guys have, yeah, you had it. Did you make your other, Carson? You guys made that one first. Can you make the other one? Yeah. Okay, very good. All right, let's take a look up here. Everybody look on the screen. So here's what chemists do, and I really like this because we know this is CH4, and there's really no hiding that. There's no way, it is just CH4. That's easy. But what about this guy here? And what they're going to do is they're going to do this, CH3OH. Now, they are not going to go, yes, the molecular formula would be CH3O, or H4O, okay? Yes, the molecular would be that, but no organic chemist would ever write methanol like that. They would all write it like this. Because guess what? They want you to know that it's an alcohol. You see that? Let's go here. How about ethanol? How would they write the graphic formula of ethanol? And it would be CH3, CH2, OH. And that would let me know that it's an alcohol, has 2 carbons in it. That's ethanol. Now, I have a very, very hard question. And I know we're running, we're okay so far. But this is a hard question. They do not call this hydroxide. They call it hydroxyl. What's the difference between this OH and the OH you might find in NaOH? Do you think an alcohol would be a base like NaOH is a base? All right, what do you think?
Is it because it's bonded to a carbon?
One more time.
Because it's bonded to a carbon?
Keep going.
Like, does that make it special?
So what?
Does that make it special? It's bonded.
We're getting there. What's the difference between that OH and the OH found in NaOH? You got pretty close. Let me ask you this. Do you think that would be a base? NaOH is a base. Why wouldn't this be a base? And this is a hard question.
Bonded to carbon.
All right, what do you think?
Bonded to carbon, which is a non-metal,
Yeah?
and then sodium's a metal.
Okay. So? All right, anybody else? This is a hard question. If you put both your answers together, you're getting closer and closer. Yes?
It's like covalently bonded to carbon, whereas with NaOH.
And it's not coming off. And it's not coming off. What's the other one?
Oh, NaOH is an ionic bond.
So the only thing that really holds them together is plus and minus, right? And so when you put NaOH in water, the ions come apart and the hydroxide ion is free to float around. And that's why it's a base. Well, this OH will not come off. It will not come off. That's why alcohols are not acids or bases. They are neutral. Everybody got that?
So does that mean that breaking up because covalent bonds are shorter, they're breaking it up? means
And
you're gonna
ionic
get more
bonds are
energy?
actually just plus and minus nature, and you put them in water, many ionic compounds come apart anyway, don't they?
So breaking up a covalent is gonna give you more.
That's
energy.
hard. That's very hard.
But it's gonna give you more energy if this bond is
If
stronger.
I want to break that bond, I'll get a lot of energy. Okay, everybody, let's go back here now. Yes.
Can you explain that again?
Okay. So NaOH is actually, there is no covalent bond, but there is an attraction between the positive ion and the negative ion. Everybody got that? And that's called an ionic bond. But when you put it in water, water's ability to pull them apart is greater than their ability to stay together. And so the hydroxide ions that are free to flow is what makes it into a base. These are covalent bonded. They're not coming apart. You can put it in water, it'll dissolve in water, but it will not break up into ions. And without those hydroxide ions, you don't have a base there. So they are not an acid or a base, they are neutral. All right, now what you just did here is we had, the first one was what they call, I'll start using some names here, okay? This right here, one book would call that maybe N-ethanol, or they might, N means like normal, like straight chain, or they might call it 1-ethanol. So, but over here, look what happens here. What if you put the OH group, and by the way, if you put it here, isn't that the same as putting it here? Isn't that right? So if you put an OH here, it's the same as putting here. As a matter of fact, you put it here, it's the same thing. See that? So there's only one ethanol, one ethanol. But this guy would be called 2-ethanol. propanol, I'm sorry. What did I say propanol? What did I say? Wait, this is ethanol. What was I making here? Propanol, my fault. Okay, this is 2-propanol. Now, I think the 2-propanol is a better name. As a matter of fact, when I look on the catalog, when I order things for every year, that's one of the names. In your book, they call it another name. And in the grocery store, they call this by another name. What do they call it when the alcohol group is not on the end, but it's actually on the middle carbon? It's up here. There's one of the characters on Density Detective. Yes, also known as isopropyl alcohol, known as rubbing alcohol. So rubbing alcohol is propanol with the OH group on the second carbon. You get that? Yes.
Why does that make a difference?
Okay, now, even though I'm not an organic chemist, when they look at that, like the melting points and the boiling points, that does make a difference. So it really is a different compound. Hey, you did a great job today, and I thought I would get into ring structure. That's the first thing we're going to do tomorrow. We're going to build some ring structures. So, all right, have a good day. Hey,